In this episode in structural geology, my dear friends, we will be continuing our discussion on the principles and concepts of rock deformation. Before we go into the detailed discussion of the factors that control rock deformation, we shall be briefly mentioning some of the points that we discussed in detail in the previous episode. It should be kept in mind that ductile deformation, in which planar layers are deformed into folds, are examples of inhomogeneous strain, where planes become curved surfaces, straight lines become curved lines, and the values of the different parameters for longitudinal strain, angular shear and gamma or shear strain changes along any given direction within the body. Now, before we go into the detailed discussion of how the behavior of materials change with the change in several factors, let us briefly consider the situation that we have discussed earlier while discussing the various deformation structures. It has been a question in the mind of all scientists that how a material which is normally brittle, that has no ability to bend and gets crushed or ground under hammer blows, can show such intricate folds in nature. For understanding this, we are going into the discussion of the factors that control the behavior of rocks. For understanding this, we must first understand very carefully that most of the rock deformation takes place at a depth where the confining pressure and temperature are much greater than the surface of the earth. We must also remember that the deforming forces that cause the development of folds and faults in rocks act for a fairly long period of time, sometimes continuing for thousands or even millions of years. So, these are the main factors that control the behavior of rocks under directed stress. There are some other factors that control the behavior. They are the presence of pore fluids, they are the presence of anisotropy or planes of weaknesses in the rocks which are being deformed. We shall be discussing the effect of these factors one by one. Before we start discussing the effects of different factors, let us understand about the behavior of natural materials first. We can see that there are three basic types of materials that respond in different ways to the applied directed stress. One are the elastic materials or elastic substances on which any directed stress causes an instant strain or change in length and angle, and as soon as the applied stress is withdrawn, the material goes back to its original shape and size. There is a limit of this kind of elastic behavior. If the applied directed stress crosses that limit, then the material fails by rupture instantly. At the other end, there are substances which behave in a pure fluid manner, that at the application of the slightest directed stresses, they start getting deformed into a permanent change, and even if the stress is not increased, it will go on deforming continuously. These materials are pure fluids, in physical terms called Newtonian fluids or viscous substances, ideal viscous substances. In between an ideal elastic substance and an ideal viscous substance, there are the plastic materials. Plastic materials are those in which the strain is proportional to the applied directed stress up to a certain limit, but as soon as the applied stress crosses that limit, the material starts behaving permanently. The elastic part of the strain is recoverable, that when the stress is removed, the strain is also removed, but beyond the elastic limit, whatever strain occurs in the material, that is permanent. So, the plastic behavior or ductile behavior is reflected in the formation of folds in nature. Now, let us look at the factors that control the behavior of materials when subjected to directed stress. Under the term materials, we include both engineering materials like metals and rocks. To an engineer, it is important to study the behavior of materials, because to him it is essential that the material he builds up his machines with should not fail while working. To a structural geologist, the purpose of this study is slightly different. He wants to study how the structures that are formed in the rock, how they form and why they form. The first factor that controls the behavior of materials we will be discussing is confining pressure. As the temperature goes up, as the deformation takes place gradually deeper and deeper into the earth's crust, the confining pressure also increases. The temperature also increases at a rate of approximately 4 degrees centigrade per kilometer into the earth's crust up to a certain depth. This increase in temperature also modifies both the strength of a material and the behavior of it. It can be evident, we have discussed it so many times in the past episodes, that how a normally elastic, hard, compact iron rod or a glass rod which is brittle can be molded into different shapes by applying heat to it. The third factor that controls the behavior of materials is time. The effect of time, as we discussed at the beginning of this episode, that directed stresses act on rock layers for a fairly long period of time, and that has certain effect on the behavior of the rocks. The next factor that controls the behavior of materials is the presence of planes of weakness or anisotropy in the rock, and the last factor that controls the behavior is the presence of pore fluids. How the pore fluids modify the strength and the behavior of materials we will be discussing shortly. To study the behavior of rocks under increased confining pressure, several experiments have been performed by geologists who cut out cylinders from actual rocks like Solenhofen limestone and applied axial directed compressive stress to them at various confining pressures in the laboratory. It was found that while at normal temperature and pressure, a very low directed compressive stress causes the material to break, to fail by rupture as soon as it crosses a low value. As the confining pressure increases gradually, the elastic limit or the point up to which the material can behave elastically increases, and after that plastic deformation, that is permanent deformation, sets in. As confining pressure increases, the strength of the material also increases. That means it can withstand more directed stress, it can undergo greater amount of plastic deformation as the confining pressure increases. This has a reflection to the complicated folds that develop in an otherwise brittle band of marble or quartzite. The second factor, or temperature, plays a very important role in the change in behavior of materials. As we have repeated several times, a higher temperature causes the solid, otherwise elastic material to start behaving plastically at a lower directed stress, or in other words, it lowers the strength of the material, while higher confining pressure increases the ultimate strength. Temperature lowers the ultimate strength and causes the material to start behaving in a plastic manner at a much lower strength, at a much lower directed stress. Thus, it can be helpful in understanding the development of folds, results of inhomogeneous ductile deformation in rocks like granite or marble, which are normally very brittle and behave in an elastic manner. The next factor, time, is of paramount importance to geologists, because as we all know, a phase of deformation lasts for a fairly long period of time, hundreds, thousands, or maybe a few millions of years. As the lithospheric plates, large bodies of the lithosphere, move towards each other, applying a directed compressive stress to the rocks on them, the phase starts and it ends when the two plates, two segments of the plates come together and stop altogether. The very slow movement of the plates causes the deformational phase to last for hundreds or thousands of years. Let us take an example. It has been found that a stone slab used as a bench in England shows a sag in the central portion. This has been caused because for many years people come and sit on the bench, which is supported at the two ends over two iron stands. Though the weight of a single person or a few persons are not enough to cause any deformation to the thick stone slab, years and years of continued pressure on the stone slab has caused it to bend. The same thing happens in case of rock layers under the Earth's crust. But before we go into the deformation, a slow deformation at low directed stresses, let us look at another aspect of the importance of time. This is for the benefit of engineers. Engineers have studied that in metals, especially metals that make up the moving parts of a machine, the strain suffered by the moving part is not enough to cause any fracture or failure when the machine works for a few number of times. But if the stress is acted on off for a large number of times, it may cause failure or fracture. The amount of directed stress that can be applied to a machine indefinite number of times without causing any fracture or failure is called the endurance limit or fatigue limit of the material. However, to a geologist, this on-off application of directed stress is not really very important. We are more interested in the effect of a small stress, maybe below the elastic limit of the material, acting continuously over a large period of time. Again, laboratory experiments have been performed to simulate this natural process. It has been found that as soon as a load is put on a material or a slab of rock, some elastic strain takes place, and as the load continues to act, the directed stress is not enough to cause rupture, but gradually, maybe over tens of weeks, maybe hundreds of weeks, if the stress continues to act, there is some permanent deformation of the material. This type of deformation, permanent deformation in a rock material acted over by a low amount of directed stress, generally below the elastic limit, is known as creep. If creep is plotted on a time versus strain curve, there are three parts. One is the elastic strain, then we have the transient creep, then we have the pseudo viscous creep, and then we have the tertiary creep, after which generally there is rupture or failure of the material. The next factor that we are going to talk about is the presence of pore fluids. Before we go into the detailed discussion of how the presence of pore fluids affect the behavior of materials, let us go back a little and discuss about how foliations and lineations form in nature. Foliations and lineations, as we said earlier, is a product of reorientation of pre-existing mineral grains, either flaky or streaky, and the recrystallization, change in shape of flaky minerals and equidimensional minerals as well. So, this principle of recrystallization, in which an original spherical or equidimensional body is changed into a linear or elongated body, takes place following Ricci's principle. Ricci's principle states that the inherent pore fluids in a rock dissolves the material from the highly stressed portions of a body and deposits them in areas where the stress is much less, thus changing the shape. This recrystallization explains how original spherical bodies like oolites or equidimensional mineral grains change into elongated ellipsoidal shapes and define either a secondary foliation or a secondary lineation. Yes. The presence of pore fluids helps in the deformation of rock material by enhancing the process of recrystallization and imparting secondary foliations and lineations to the rocks. Geologists have also believed that the presence of other solutions that can be used to react with the rock material modifies the behavior of the material. To check this, experimental observations were made on the same rock treated with different liquid material and at dry temperature. It has been found that when a rock is subjected to a specific amount of directed stress in dry condition, there have been practically no strain even over a period of 100 days. However, when the same rock, the same sample was subjected to the same amount of directed stress in presence of water, there was considerable strain, considerable shortening within a period of 50 days, and this strain was permanent. When the same rock material was treated with dilute hydrochloric acid and subjected to same amount of directed stress, the material shortened much more quickly. Within 20 days it shortened to a great extent and failed by rupture. Thus, it can easily be seen that the strength of rock materials significantly decreases when they are subjected to directed stress under dry conditions or under liquid conditions, under the presence of liquids of varying chemical properties. The next factor that we are going to discuss about are anisotropy or planes of weakness that are present in a rock. These planar planes of weakness, they definitely control the behavior of rock material, how they will deform. To understand it better, several cylinders were cut of a limestone without any plane of weakness, and out of another rock with a prominent foliation. Of the second rock, two sets of cylinders were cut one in which the axis of the cylinder was parallel to the foliation and one in which the axis of the cylinder was perpendicular to the foliation. These three sets of samples were subjected to both axial compression and axial shortening. The experimental observations revealed that while in the unfoliated rock there was very little difference in the amount of deformation undergone by the cylinder, whether the stress was compressive in nature or extensional in nature. In the second case there were significant variations. In case when the cylinders were cut perpendicular to the foliation, extensional stress very easily caused permanent deformation, while those cylinders could withstand a far greater directed stress when the stress was compressive. When the cylinders were cut parallel to the foliation, it was the reverse. It was found that the cylinders cut parallel to the foliation could withstand a much higher extensional stress than a directed compressive stress. Since many of the rock materials that we see in nature have some primary foliations or primary planes of weakness within them or secondary planes of weakness which have been subjected to repeated deformation, the existence of these weak planes definitely change the behavior of the rock, change the strength of the rock, the amount of strain that it can withdraw before failure, the amount of directed stress it can withstand ultimately. Rock deformation or rock strain always takes place at depths in the earth's crust. The higher confining pressure, temperature, presence of pore fluids, presence of solutions, chemically active solutions, presence of planes of weakness in the rocks variously affect the behavior of materials and the development of ductile and brittle structures in the rock. When a rock layer is subjected to directed stress, the factors that control the structure which will form in a rock are, apart from the amount of directed stress and physical properties of the materials, the ambient factors. We have seen by the experiments that were conducted on actual rocks by several workers at how the behavior of rocks, the strength of the rocks, the point at which permanent deformation takes place, the point up to which the rock can bear a directed stress variously gets modified in the presence of higher confining pressure, high temperature, in the presence of pore fluids, in the presence of solutions, and most importantly time, which is geologically very significant. These all points had to be taken into consideration before he starts analyzing the tectonic scenario of a terrain. Another aspect of these experiments, which were performed under the same confining pressure and same directed stress for different materials, it was found that various materials act in different ways. While a sedimentary rock starts behaving plastically at a fairly low confining pressure, a metallic sulfide mineral like pyrite can behave elastically up to a fairly high amount of directed stress and then fail by rupture. Now we come to the end of this episode. Let us discuss what we have learned over this episode and the previous one. Over these two episodes we have discussed how rock deformation takes place. In the first episode we discussed what causes the rocks to get deformed, the definition of stress, strain, various ways of measuring strain, and how the strain and actual rock structures can be correlated. In this episode, we have discussed in certain detail about the factors apart from the amount of directed stress and the rheological property of the material that is being deformed. We have discussed in detail how the various physical factors like confining pressure, temperature, time, anisotropy and presence of fluids affects the behavior of material. This will help us in understanding the ductile and brittle structures that are found in a deformed rock much better. In our next episode, we are going to discuss about the analysis of geological structure. The main job of a structural geologist is to go to the field, measure the orientation of the structures and start to find out how these structures came into being. Our next episode will be dedicated to the analysis of geological structures, but before we start analyzing geological structures, we would be learning about the ways of analyzing geological structures, the techniques that we use. We will be discussing about stereographic projections to analyze geological structures in our next two episodes.